This is a quick overview of the history of the atom, or at least the history of the modern electron cloud model of the atom, because, as far as we know, the atoms themselves go back to the Big Bang, but that's a whole nother astrophysiological, theological, something kind of debate. So we'll skip over that for today and we'll start way back when we just had Democritus back in Greek times that said, hey, matter is made of particles. And so if I've got something of matter, it's made of all these particles, and they didn't really know what the particles were. If we go back to Greek times, we can have the various elements. What were the four Greek elements? Earth, wind, air, and fire that made it up. So somehow everything was made up of particles of those. But it was more of a little bit of street corner philosophy than it was really a scientific development into the nature of matter. And it wasn't for a long time until John Dalton comes up with his what's often called the billiard ball model. And I guess I can't draw a ball, but we'll draw our cue. Billiard ball model, in that we have these ball-shaped structures that make up matter, and these end up kind of coining Democritus's language with calling them atoms. But Dalton basically says that if you have an iron atom, that every other iron atom is exactly identical to it. And we now know that that's not necessarily the case, because we can have different isotopes of iron. And even though those all have the same number of protons and chemically behave the same, they actually have different masses. And this particular little problem was one that was probably the last of the little mysteries of the atom that was figured out according to the modern electron cloud model, but it was just kind of for a long time known as Dalton's mass problem. So Dalton did define the element, but had a little bit of a mistake in saying that all atoms of an element are identical, and they really are, except for their masses. So this kind of triggers a lot of research into, okay, what is the nature of the atom? What makes it up, kind of like we're doing today, where we now have protons, neutrons, and electrons, and we're trying to figure out what makes them up. Really, that same sort of work happened in trying to figure out what makes up Dalton's elements. And so there were lots of different pieces along the way that came along. Millikan characterizes the nature of the electron, particularly its mass, and that it's extremely small. You got Benjamin Franklin previously had thrown in pieces about opposite charges and opposites attracting. You've got Antoine Lavoisier's work comes in here about that matter is not created or destroyed, and Lavoisier really was looking specifically at chemical changes. We know now that that applies to physical changes, and but not nuclear changes. And then along comes old J.J. Thomson, and J.J. Thomson says, all right, here is the atom. The atom is this kind of field of positive material. And then within that field of positive material, you have these little embedded bits that are these electrons that Millikan characterizes. This is what's often referred to as the plum pudding model. And what is plum pudding, you say? Well, unless you're very British, you probably have no idea. And it's been a long time since I've had anybody in chemistry class that didn't have a last name of Belk that had actually had plum pudding. Plum pudding is a British dish. The closest thing that I can relate to is a blueberry muffin. And so in a blueberry muffin, you kind of have the muffin part, and then within that you have the various blueberries. And so the blueberries would be the equivalent of the electrons, and then the muffin, light and fluffy and sweet, surrounding it would be the positive material described by J.J. Thomson. So the electrons are kind of fixed in this positive material. And it seemed to work, positives and negatives attracting, they're stuck together, but it didn't describe a lot of things. And it wasn't until Ernest Rutherford comes along and he does his gold foil experiment that things really begin to change. And I'm going to leave it to another video to demonstrate Ernest Rutherford's experiment, so you can watch that, either stop now or come back to it later. But basically, Rutherford fired some particles at gold foil. And what we'd expect if Thomson's model was correct is we'd have a lot of interaction of the particles with the gold foil. The particles that Rutherford used were actually alpha particles, which we studied about in radiation. That is a helium nucleus, so they've got some mass to them and they're positively charged. So we'd expect there to be some energetic collisions, and we'd expect the alpha particles to bounce off of anything that was positive. But what Rutherford actually found was that almost all of the particles that he fired at this gold foil, almost all of them went straight through unaffected. Few of them deflected off, few of them bounced various places, but almost all of them went straight through the gold foil unaffected. And so the conclusions that we get out of that, and the other video explains a little bit more, is that the atom is, I've got to change my pen color here. The atom is mostly empty space, that it has a dense, compact nucleus, and the nucleus is positively charged. We know that because the alpha particles bounced off, which means they had a like charge, that the nucleus is dense because the alpha particle bounced off of it and not the other way around. The alpha particle didn't knock it out of the way. But because most of the particles pass straight through, Rutherford concludes that the atom is mostly empty space. So out of this, sorry, JJ, but whether you call it the plum pudding model or the blueberry muffin model, it's just not right. So this is a huge turning point. I mean, Rutherford's experiment is like a big deal, the big deal. It's really the beginnings of modern chemistry. And then a whole bunch of other work takes place. Rutherford's colleague, Neil Bohr, starts to try and work out the actual nature of the electron cloud. So you have this small nucleus that's positive, and then Bohr essentially envisioned that the electrons would be orbiting around the nucleus like planets, and so you end up with what's often called the Bohr model of the atom, which shows them like this. Whoops, my notability. That shows them like this. However, this doesn't really allow for the nature of molecules as we know them to be. Plus, the problem with Bohr's model is that it requires very specific paths to be followed by the electrons. And Heisenberg, Werner Heisenberg, is really the one that comes in and causes trouble because he develops what's called his WH's uncertainty principle. And basically, Werner Heisenberg's uncertainty principle states that because electrons are so small, so light, and so fast, that just the act of trying to bounce a beam of light off the electron to view it would move the electron. Or basically, you can never be certain about where an electron is. You just know where it should be. So you can describe a region where the electron would exist, but you cannot define a specific orbit, a specific path, a specific location of an electron at any one time. So, kind of like, well, gee, just because you can't pinpoint it, does that mean Bohr's wrong? Well, ultimately, it's Erwin Schrödinger, which I think I pronounced that right, Erwin Schrödinger, who's famous for his cat in a box thought experiment. The idea that if you if you, and this was a thought experiment, not real, but the thought experiment of if you put a cat in a box with a bottle of poison and sealed the box, that the cat may be alive or dead because either the cat drank the poison or it didn't. And therefore, if the cat could be either alive or dead, then it might as well be both alive or dead at the same time. Does it really make a difference? And so this is one of those things philosophers do, is they sit and think about these things. So if you enjoy to just sit around the campfire and think about things like this, by all means, be a philosopher. It was not my best grade in college, though, because I'm very about give me literal direct observations. Just open the box and tell me what the cat is doing. Hopefully it's alive. Um, but so where Schrödinger really excelled, though, was mathematics. And Schrödinger developed an equation that partly took Bohr's model, this idea of that the electrons around the nucleus occur in specific levels of energy. So we might call these energy levels, or we ultimately call them orbitals. And Schrödinger took all of the different properties that these energy levels should have. You know, X, Y, and Z axes, energies, all sorts of different influences, and he put them into what's known as the Schrödinger wave equation. And you know how, for those of you that have done some algebra, you know, you can take, and if you have an equation such as y equals mx plus b, then you plot that on your XY graph and you end up with a line of some sort, or that sort of line, or that sort of line. That if you, and for those of you that are really far along in math, you know, if you have something like y equals ax squared plus bx plus c, you end up getting something that, you know, is the parabola shape. So each equation has some sort of a shape if you graph it. And what Schrödinger predicted in his wave equation is that if you plug in all of the different parameters for a specific electron at in a specific element, so like this one electron in our hydrogen atom here, that if you plot in all the characteristics that you'd expect to have of that, you get a shape. And those shapes are called the atomic orbitals. And so all of these little pictures that you see here shaded in this SPDF orbital diagram are the outputs of Schrödinger's wave equation for all of the various possible electron locations outside the nucleus. And so as you add electrons in, you kind of form a repeating pattern of these shapes that, you know, each little orbital can have, you know, so many different electrons in it. And then when you take and you have an atom that has all sorts of these orbitals, they add up into these really cool, looks like one of the street performers down at Faneuil Hall had made very complicated little balloon animals out of it. But so you end up coming up with all these interesting shapes, and these shapes predicted by Schrödinger's wave equation actually do fit the model of the shapes of molecules that we see form. And now that we even have some technology to actually observe the outer surfaces of electron clouds, scanning tunneling electron microprobes and things like that, we actually see that atoms do have shapes much like these to their electron clouds. They're not truly clouds, but they're just regions where the mathematics says somewhere inside this little sphere, that is where this particular type of electron will exist. It's a region of probability where if you looked, you would find the electron there, except that Heisenberg said, well, you're never really going to directly find one electron, but we'll let that slip. So these shapes really represent, and the best visual representation you can get, these kind of collective drawings over here. These are what the electron cloud really looks like according to our best information. So at this point, we have an atom with a positively charged, dense, compact nucleus. We have electrons that are occurring in these that are occurring in these regions of probability that we call orbitals. But notice one thing that's missing is we still have a nucleus that's just positive. And it's not until Chadwick ultimately comes along and solves the final problem as we start to head into the realm of nuclear science. He says, hey, the nucleus isn't just a positive thing, it's a positive and neutral core to the atom. So there are positive particles. Those end up being called protons. Rutherford named those after another scientist named Prout, plus the fact that pro is usually reference to positive. But Millikan recognizes, hey, there's this neutral particle. It gets called the neutron because it's neutral. And now we have the overall modern structure of the atom where the nucleus contains protons and neutrons, and then around it, in this region of probability with all these really cool, interesting shapes, we have the electrons. And that is the story of how we arrive at the modern electron cloud model of the